Linear algebra, examples of linear independence and dependence. Consider this. The set of vectors in R3, 1, 0, 1, 3, minus 1, minus 2, minus 5, 1, 0. Are they linearly independent or are they linearly dependent? The answer is they are linearly dependent. I.e., they are not linearly independent. Why? Because we can find a way to go nowhere, i.e. take some non-zero scalars of the vectors in the set and still sum to 0. I.e. there's a combination of these vectors, a combination which isn't 0 times this vector plus 0 times this vector plus 0 times this vector, which still yields 0. Now what is that combination? Well, it turns out it's 2 of the first vector plus 1 of the second vector minus 1 of the third vector. Why is this true? Let's just check it's the case. Well, take the first top line. 2 times 1 plus 1 times 3 minus 1 times 5. What's that equal to? 2 plus 3 minus 5, 0. Same here. 2 times 0 plus 1 times minus 1 minus 1 times minus 1. What's that equal to? Well, that's 0. Minus 1 plus 1, 0. Third line. 2 times 1 plus 1 times minus 2 minus 1 times 0 is equal to 2 minus 2 plus 0 is 0. Now let's take a step back here and think about what we've just shown. We've just shown that these three vectors, when you take 2 of this vector plus 1 of this vector minus 1 of this vector, you get 0. Now this is really important. Why is it important? It's important because we've now found an example of non-zero elements, non-zero scalars, which sum to 0. Therefore, these vectors are linearly dependent. In some ways, we've started at an origin, we've left the origin, and made our way back. The second example we will consider is this one. It's a set of 2, 3, 3, 0, minus 1, 2, 0, 0, 3. Is it linearly independent or linearly dependent? Well, it turns out it's linearly independent. Thus we have... Now how do we know this? Well, let's just consider this equation. So we have our three vectors and we're adding a scalar to them. If these vectors are linearly dependent, then there will be some non-zero solution to this, i.e. we can find at least one of these numbers to be non-zero and still get 0 here. If the solution to this equation is to have each of the AIs equal to 0, i.e. that's the only solution, then these vectors are linearly independent. So how are we going to decide whether it's linearly independent or dependent? Well, the first thing we can do is we know that, take the first line of this equation, just like we did before. We know 2AI is equal to 0. Therefore, AI is equal to 0. We also know that A2 minus 1 is equal to 0. Why is that true? Well, we know that 3AI plus minus A2 is equal to 0 because it's 0A3. Now look at this. We know A1 is equal to 0. These are A1s. A1 is equal to 0. Therefore, 3 times 0 minus A2. Therefore, A2 is equal to 0. Similarly here, we have 3a1 plus 2a2 plus 3a3 is equal to 0. But a1 is equal to 0, a2 is equal to 0, therefore a3 is equal to 0. The key thing to realize here is the definition of linear independence and linear dependence. With linear dependence, there is a non-zero set of scalars, i.e. at least one of these a1, a2, a3 is not equal to 0, but still yields 0 here. With linear independence, the only solution is when a1, a2 and a3 is 0.